Right now, a dwarf planet less than a fifth the mass of our moon, 5.8 billion kilometers away, is actively refrigerating its own sky. Surface temperatures sit around minus 230 degrees Celsius, more than 300 degrees colder than anywhere on Earth, and yet beneath that frozen shell, a liquid ocean may still exist. This same world has been quietly leaking the building blocks of life onto a neighboring moon for 4 billion years. Most headlines told you Webb photographed Pluto. The part they skipped is far stranger. Stay with me, because by the end of this video, you will understand exactly why one frozen world is forcing scientists to rethink how planets work. And hit subscribe now, because this channel breaks down real discoveries without the exaggeration, and you do not want to miss what is coming next. Let's go back to where this story begins. In 1930, a 24-year-old farmhand from Kansas named Clyde Tombaugh arrived at the Lowell Observatory outside Flagstaff, Arizona, carrying no university degree and almost no formal training. What he did carry was a set of detailed pencil drawings of Jupiter and Mars, sketched by hand through a homemade telescope he had built himself, using mirrors he ground and polished on his family's wheat farm. Those drawings impressed the observatory staff enough to offer him a job, though the position itself was anything but glamorous. Tombaugh was assigned one of the most tedious tasks in all of astronomy. Night after night, he photographed the same patches of sky on glass plates, then loaded them into a device called a blink comparator, a machine that let him flip rapidly between two images of the same star field taken on different nights. If anything had moved, it would appear to jump back and forth while everything else stayed still. The work demanded extraordinary patience. Tombaugh sat in an unheated dome through Arizona winter nights, eyes pressed against the comparator for as long as 14 hours a day, scanning thousands of star images, one tiny section at a time. Most nights produced absolutely nothing. Then, on February 18th of that year, something moved. A faint dot had shifted position against a background of fixed stars. That dot was Pluto. If you shrank the entire solar system down to the size of a football pitch, Pluto would sit somewhere beyond the fence in the parking lot, and it would be smaller than a dried pea. That is the scale of what Tombaugh found, using nothing but glass plates and his own eyes, nearly a century ago. For the next 76 years, Pluto held the title of the 9th planet in our solar system. School textbooks printed its name alongside Mercury, Venus, Earth, and the rest. Children memorized it. Scientists referenced it. But almost everything the public believed about Pluto during that stretch was built on guesswork, layered on top of more guesswork. Early estimates wildly overstated its size, because astronomers assumed Pluto needed to be massive enough to explain certain gravitational wobbles in the orbits of Neptune and Uranus. Those wobbles turned out to be measurement errors, not real influences from Pluto at all. For most of the 20th century, even the largest telescopes on Earth could not resolve Pluto as anything more than a tiny, blurry smudge. Nobody knew its true diameter, nobody knew what its surface looked like, and whether it even had an atmosphere remained a genuinely open question for decades. It was not until the 1990s that Hubble finally produced a handful of pixels, barely enough to show rough patches of light and dark, and nothing close to real detail. Then, in 2006, the International Astronomical Union held a vote and formally reclassified Pluto as a dwarf planet. It remains the only world in recorded astronomical history to be discovered, celebrated for 3/4 of a century, and then officially voted out of the very category that once defined it. For a long time after that, the story felt finished. Pluto was small, distant, and easy to file away as unimportant. That assumption did not survive contact with real data. In July of 2015, after a journey lasting 9.5 years across billions of miles of empty space, NASA's New Horizons spacecraft arrived at Pluto, traveling at more than 50,000 kilometers per hour. The radio signal confirming the spacecraft had survived its closest approach took 4.5 hours to reach Earth, traveling at the speed of light the entire way. Engineers at the Johns Hopkins Applied Physics Laboratory sat in near silence for almost 5 hours, waiting to learn whether the mission was still alive. New Horizons had exactly one chance. No orbit, no second pass, just a few minutes to capture everything it possibly could before continuing into the Kuiper Belt forever. What it sent back completely shattered expectations. A massive heart-shaped plain of frozen nitrogen stretched across the surface, smooth and strangely young-looking. Mountains of solid water ice rose more than 3,000 meters into a thin, hazy sky, frozen so hard that the ice behaved less like ice and more like granite. Beneath the surface, nitrogen appeared to be slowly churning in enormous convection patterns, suggesting heat and motion in a world scientists had assumed was completely dead. Pluto was not a frozen leftover. It was active. But New Horizons only got one look. It captured what it captured, then kept flying deeper into the outer solar system, never to return. Whatever it missed during that single pass would remain unknown for years. Scientists needed a completely different kind of instrument. Not one that flies past and snaps a photograph, but one that can read the chemistry of a world from billions of miles away without ever leaving its orbit around the sun. That instrument was already being built. The James Webb Space Telescope does not work the way most people imagine. It does not fly toward its targets. It does not take photographs in the way a camera on your phone does. What Webb actually does is read light itself. It collects the faint glow arriving from an object billions of miles away and splits that light apart into its individual wavelengths, the way a prism breaks white light into a rainbow, except with far greater precision and across wavelengths your eyes could never detect. Each molecule leaves its own specific pattern in that light, a chemical fingerprint that tells researchers exactly what substances are present, how warm they are, and how they are behaving. If a regular camera takes a picture of a cake, Webb tastes every layer separately, the flour, the sugar, the eggs, and tells you the exact oven temperature and how long it baked. Pointing this instrument at Pluto presented a challenge that had frustrated astronomers for years. Pluto and its largest moon, Charon, sit so close together in the sky, from Webb's vantage point 1.5 million kilometers from Earth, that earlier generations of telescopes could never cleanly separate the thermal signal of one from the other. Every attempt came back muddled, two heat sources blurred into one. Webb's primary mirror, 6.5 meters across, combined with its mid-infrared instrument, finally solved that problem. For the first time, scientists could isolate Pluto's own faint thermal signature and read it cleanly. To put the difficulty in perspective, from Webb's position, Pluto appears smaller than a grain of salt held at arm's length, and yet Webb can read the chemistry of that grain with enough precision to reshape what we know about an entire world. Starting in 2022, once those instruments were fully calibrated, Webb turned its attention toward the outer solar system. And what has come back over the years since has not simply been a prettier picture, it has been closer to a full diagnosis, revealing a set of behaviors so unusual that researchers are still working out exactly how to explain some of them. The first major finding involves the blue haze that New Horizons first photographed during its flyby in 2015. Scientists already knew Pluto's thin atmosphere was wrapped in a delicate layer of hydrocarbon particles, tiny grains suspended high above the surface. What nobody had confirmed was what that haze was actually doing to the climate beneath it. Back in 2017, a planetary scientist named Shi Zhang, working at the University of California, Santa Cruz, proposed an idea that sounded almost backwards at the time. On Saturn's moon Titan, atmospheric haze traps heat and warms the world below it, acting like a blanket draped over the surface. Zhang argued that Pluto's haze might be doing the exact opposite. His calculations suggested that those tiny hydrocarbon particles were absorbing sunlight during the day and then radiating that energy straight back out into space as infrared heat, faster than Pluto's extremely thin atmosphere could ever hold on to it. The haze was not acting like a blanket. It was acting like a radiator, actively bleeding warmth away from a world that already had almost none to spare. When Zhang first published this idea, many of his colleagues were skeptical. The concept made theoretical sense on paper, but there was no instrument sensitive enough to actually test it. Nobody could measure Pluto's atmospheric temperature precisely enough to confirm whether the cooling effect was real or just a mathematical curiosity. The idea sat waiting. That changed once Webb's mid-infrared instrument came online. A team led by astronomer Tongai Bertrand at the Paris Observatory used that instrument to measure Pluto's upper atmosphere directly, cleanly separating its signal from Charon's for the first time. The results, published in the journal Nature Astronomy in June of 2025, confirmed almost exactly what Zhang had predicted 8 years earlier. Pluto's upper atmosphere is roughly 30 degrees Fahrenheit colder than earlier models had expected, and the haze particles suspended within it are the reason why. This is not simply a case of Pluto being cold because it sits far from the Sun. Every planet far from the Sun is cold. What makes this different is that Pluto is actively making itself colder. The haze in its own sky is working against it, pulling heat away faster than the thin atmosphere can retain it. On Earth, our atmosphere traps heat through the greenhouse effect, keeping the surface warm enough for liquid water and life. On Titan, haze does the same thing, holding warmth in. On Pluto, the haze does the opposite. It vents heat into space. Scientists now describe this as a genuinely new kind of climate mechanism, one that behaves differently from every other atmosphere we have studied anywhere in the solar system. Imagine pulling a blanket over yourself on a cold night, except this blanket does not keep you warm. Instead, it actively pulls heat out of your body and pushes it into the room around you, leaving you colder than if you had no blanket at all. That is what Pluto's haze is doing to an entire world. Pluto is not just cold, it is actively refrigerating itself. Let that sit with you for a moment. If you are the kind of person who actually wants to understand how space works instead of just reading clickbait headlines, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. But the haze is doing something else, something that connects this frozen dwarf planet to a question humans have been asking for centuries. Even the extremely faint trickle of sunlight that reaches Pluto, roughly 1,000 times weaker than sunlight reaching Earth, is enough to break apart methane molecules high up in its atmosphere. Those broken fragments do not simply vanish, they recombine into heavier compounds, triggering a slow chemical cascade that builds progressively larger and more complex molecules. The end product is a substance known as tholins, reddish-brown organic particles that drift slowly downward through the haze and settle onto the frozen surface below like a kind of snow. That snow has been falling continuously for roughly 4 billion years. The term tholin was coined by astronomer Carl Sagan and his colleague Bishun Khare at Cornell University, first published in the journal Nature in 1970. Sagan and Khare created these substances in their laboratory by taking simple gases known to exist throughout the solar system, nitrogen and methane, and bombarding them with ultraviolet light. The result was a sticky, reddish-brown residue unlike any naturally occurring material on Earth. They needed a new word for it. On Pluto specifically, Michael Summers, a planetary scientist at George Mason University and a member of the New Horizons science team, co-authored a study titled "The Photochemistry of Pluto's Atmosphere as Illuminated by New Horizons," published in the journal Icarus. Summers estimated that the layer of tholins accumulated on Pluto's surface could be 10 to 30 meters thick in some regions, providing more organic material per square meter than an entire forest on Earth. That is not a poetic exaggeration, that is a direct calculation based on the rate of production and the age of the surface. Tholins belong to a broad family of complex organic molecules built from carbon, nitrogen, and hydrogen. They are not alive, but they are precisely the kind of raw chemical building blocks that some scientists believe may have once rained down onto early Earth, delivered by comets and asteroids, contributing the starter material for the chemistry that eventually led to life. When tholins come into contact with liquid water, they can produce amino acids, the fundamental units from which proteins and eventually living organisms are built. This connects directly to one of the largest ongoing debates in the study of life's origins. Did the first organic building blocks form right here on Earth's surface, cooked up by lightning and volcanic heat in our own early atmosphere? Or did at least some of that raw material arrive from space, carried in by impacts from icy bodies where the same photochemical processes had been running for billions of years? Scientists still do not agree. But Pluto offers something no other world can. It is a real, active, ongoing example of exactly that chemistry running continuously on a planetary surface right now, producing the same kinds of molecules that on Earth may have helped spark the transition from simple chemistry to biology. On Earth, that process ended billions of years ago. Whatever happened in those early oceans left behind only indirect traces buried in ancient rocks and fossils. On Pluto, the tape is still playing. A world manufacturing the ingredients of life and scattering them across its own frozen surface, decade after decade, century after century, for 4 billion years without pause. And here is the part that stays with you. Everything life needs to begin is sitting right there. The organic molecules are there. The raw chemistry is there. The slow, continuous supply is there. Everything except warmth. Pluto's surface is so cold that nitrogen, the same gas that makes up most of the air you are breathing right now, freezes completely solid. The atmosphere you are sitting in as you watch this video would, on Pluto, simply become part of the frozen ground. It is a world permanently stuck at the step just before life could ever begin, a kitchen stocked with every ingredient you could ask for, flour, eggs, sugar, arranged neatly on the shelf for 4 billion years, but the oven has never once been turned on. Everything life needs to begin is there. Everything except warmth. And here is where the story takes a turn that genuinely unsettled the researchers who first confirmed it. Pluto has been slowly leaking into space for billions of years. Methane and other light molecules drift upward through its thin atmosphere, slip past its weak gravity, and escape outward. Scientists suspected this was happening, but for a long time nobody knew where all of that escaping material was actually going. It was not simply vanishing into empty space. Something was catching it. Pluto's largest companion, Charon, roughly 1,200 kilometers across, orbits about 19,000 kilometers away. Most of Charon's surface is fairly unremarkable water ice, ancient and heavily cratered, except at its poles, which are stained a deep, unmistakable reddish-brown, darker than anything else visible on the Moon. Will Grundy, an astronomer at Lowell Observatory, led the key research confirming what was happening, published in the journal Nature in 2016. Methane escaping from Pluto's atmosphere drifts across those 19,000 kilometers of empty space, gets captured by Charon's gravity, and lands on its surface. but it does not land just anywhere. Because of the extreme tilt of the Pluto-Charon system, Charon's northern polar region spends multiple decades at a time in complete darkness, with no sunlight reaching it at all. That makes the pole an extremely effective cold trap. Methane molecules arriving from Pluto encounter that darkness, freeze solid onto the surface immediately, and sit there, accumulating year after year, decade after decade, with nothing to disturb them. When sunlight finally does return, it does not simply melt the frozen methane away. Ultraviolet radiation and cosmic rays break the frozen molecules apart and reassemble the fragments into heavier, more complex reddish-brown compounds. Those heavier molecules cannot evaporate back into space. The color is locked in permanently. Grundy's team estimated that roughly 30 centimeters of tholins would accumulate on Charon's poles over the moon's billion-year lifetime, building up layer by layer in a process running since long before either world had a name. Then, in October of 2024, a team led by researcher Sylvia Protopapa at the Southwest Research Institute used Webb data to confirm something nobody had ever detected on Charon before. Frozen carbon dioxide, the same gas leaving your lungs with every breath, and hydrogen peroxide, the same compound sometimes used to disinfect a wound, were both present on the surface. The carbon dioxide most likely came from underground material exposed by impact craters. The hydrogen peroxide appears to have formed through years of radiation, slowly rearranging Charon's water ice into something new. Pluto and Charon do not orbit each other the way Earth and its moon do. They are so close in size that they orbit a shared point in empty space between them, a center of gravity that sits outside Pluto's surface entirely. Each one always shows exactly the same face to the other, locked in a permanent mutual gaze. And across those 19,000 kilometers of vacuum, atmosphere and color have been quietly passing back and forth for longer than complex life has existed anywhere on Earth. No one commanded this exchange, no one designed it. It is a chemical dance that started on its own and has been running in absolute silence for billions of years, two worlds slowly painting each other in the dark, and nobody knew until we finally had the right pair of eyes to look. If you have found this as strange and fascinating as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. But there is one more thing hiding on Pluto, and this one is the hardest to accept. South of that famous heart-shaped plain, two enormous peaks rise out of the surrounding landscape. One stands roughly 4,000 meters tall, the other may reach close to 6,000 meters, with a base wide enough to rival some of the largest volcanoes on Earth. Both mountains have deep depressions at their summits, ringed by fractures, with lumpy, uneven flanks that closely resemble cooled lava flows. Except there is no molten rock on Pluto. If these features are what they appear to be, they are cryovolcanoes, structures that once erupted, not with melted stone, but with a thick slurry of water, ammonia, and methane forced upward from somewhere deep beneath the icy crust. Something, at some point in Pluto's history, was warm enough down there to push liquid material all the way to the surface. Cracks and ridges scattered across the surface line up in patterns consistent with what you would expect from a subsurface layer of liquid water shifting slowly beneath the crust. Sputnik Planitia, that enormous heart-shaped basin, sits directly above what appears to be a positive gravity anomaly, a spot where something denser than the surrounding ice may be concentrated underneath. Francis Nimmo, a planetary scientist at the University of California, Santa Cruz, and a member of the New Horizons science team, developed the subsurface ocean scenario based on that gravity anomaly, publishing his analysis in the journal Nature in 2016. Then in 2020, Carver Beerson, also at UC Santa Cruz, published a study in Nature Geoscience that went further. Bierson's team demonstrated through numerical simulations combined with geological observations from New Horizons that Pluto may not have started cold at all. Their evidence suggested that Pluto formed rapidly and violently enough to begin its life hot, with a subsurface ocean present almost from the beginning, 4.5 billion years ago. Not an ocean that developed later as radioactive decay slowly melted the ice, but one that was there nearly from day one. Separately, Shunichi Kamata of Hokkaido University, working with an international team spanning institutions in Japan and the United States, published research in Nature Geoscience in 2019 showing how that ocean could still be liquid today. Their computer simulations revealed that a layer of gas hydrates, crystalline ice-like solids that trap gas within molecular water cages, could sit between the ocean and the outer ice shell, acting as a natural insulating blanket. Gas hydrates have extremely low thermal conductivity. They do not let heat pass through easily. Kamata's models showed that this insulating layer could keep the ocean from freezing for hundreds of millions of years, and quite possibly right up to the present day. Think of it as a hot water bottle that warms itself from the inside, placed in the middle of a freezer, slowly maintaining a thin layer of liquid water between a warm rocky core and a frozen outer shell, for billions of years, without any help from a star. Similar hidden oceans are already strongly suspected beneath the icy surfaces of Europa and Enceladus, but both of those moons are larger than Pluto and sit much closer to the Sun, warmed by powerful tidal forces from the giant planets they orbit. If a body as small and as cold and as distant as Pluto turns out to be hiding something similar, it would mean subsurface oceans are not a rare exception limited to a few moons with special circumstances. They could be common across hundreds or thousands of icy bodies throughout the outer solar system. As Nimmo himself put it, when we look at those other objects in the Kuiper belt, they may be equally interesting, not just frozen snowballs. But it is important to be honest about what we do not know. No spacecraft has drilled beneath Pluto's surface. No ice-penetrating radar has confirmed liquid water directly. Some researchers argue that the surface features could be explained by other mechanisms that do not require an ocean at all. One simulation of how Sputnik Planitia formed suggested the basin could have been created even if Pluto's interior were completely solid. And media coverage has a habit of leaping from may have an ocean to life on Pluto, a jump that is not supported by any current evidence. William McKinnon, a professor at Washington University in St. Louis and a co-investigator on the New Horizons mission, described what any ocean down there would actually be like: extremely cold, extremely salty, rich in ammonia, almost a syrup. No place for germs, he said, much less fish or squid or any life as we know it. But even the most cautious, most conservative reading of this evidence still leaves you with a world that no scientist expected. A dwarf planet at the edge of the solar system that runs its own climate in reverse, manufactures the raw building blocks of biology and scatters them across its surface for 4 billion years, leaks its atmosphere onto a neighboring moon, and paints that moon a different color, and may still be holding liquid water beneath a shell of ice harder than granite. Even the most cautious version of this story is stranger than what any scientist imagined before we actually looked. Picture for a moment what it would actually feel like to stand on Pluto's surface right now. The sun is still visible, but only as an intensely bright point of light, smaller than the head of a pin, held at arm's length. You could stare directly at it without any discomfort at all. No glare, no warmth, just a sharp white dot hanging in a sky that never fully brightens and never fully darkens, a permanent grayish-blue gloom thick with haze, as though someone dimmed the world to a perpetual twilight and forgot to turn it back up. The ground beneath your feet does not behave anything like ice does here on Earth. At minus 230 degrees Celsius, water ice stops being slippery, it stops being fragile, it becomes something closer to solid rock, hard enough to ring almost like metal if struck. You could tap your boot against it and hear a sharp, clean note bounce back, surrounding you in every direction. Towering blades of frozen methane rise from the surface like the teeth of an enormous saw, some reaching as high as a 150-story building, arranged in long, jagged rows stretching toward the horizon. You would not walk through them, you would stand at their base and look up. The cold does not creep in slowly. Exposed skin would freeze almost instantly, faster than your body could register the sensation, faster than you could begin to shiver. The atmosphere around you is 100,000 times thinner than Earth's. There is nothing to breathe, but the cold would reach you long before the lack of air became the immediate problem. And overhead, fixed permanently in the same spot in the sky, Charon hangs there, unmoving. The two worlds are locked so tightly that each one always shows exactly the same face to the other. If you looked up carefully, you could see the reddish-brown stain on Charon's pole with your own eyes, the color that came from the very atmosphere surrounding you right now. Carried across 19,000 kilometers of vacuum and frozen permanently into another world's surface. If you stood still long enough, you would notice something else. Drifting down from the haze above, finer than dust, reddish-brown particles settling on your helmet and shoulders. Tholins, the building blocks of life, falling like snow onto a world too cold for any of it to ever wake up. This scene has barely changed in millions of years. If you came back 10 million years from now, nearly everything would look exactly the same. Pluto is not unique simply because of what it is. It is unique because of where it sits and what that location implies about everything else around it. The Kuiper Belt, the vast ring of icy debris beyond Neptune where Pluto makes its home, spans a region of space hundreds of times larger than the much more familiar asteroid belt sitting between Mars and Jupiter, the one most people picture when they think of a field of space rocks. But unlike that inner belt, which has been mapped in close detail thanks to its proximity to Earth, the Kuiper Belt remains almost entirely unexplored. It contains hundreds of thousands of objects wider than 60 miles, along with an estimated trillion or more comets drifting through the darkness. A handful of other bodies out there, including Eris and Makemake, come reasonably close to Pluto's size. Beyond the Kuiper Belt entirely lies the theorized Oort cloud, thought to hold another trillion or so icy bodies stretching outward roughly a quarter of the way toward the nearest star. And in all of that space, only one spacecraft has ever ventured deep enough to closely photograph any of it. New Horizons managed close flybys of exactly two objects, Pluto and a much smaller body nicknamed Arakoth, out of the hundreds of thousands of similarly sized worlds believed to exist out there. Two objects. Out of hundreds of thousands. That is not exploration. That is barely a glance. Right now, Webb continues to check back in on Pluto every few months, whenever the dwarf planet swings into its field of view. Each time it adds another data point, and almost every time the overall picture becomes stranger than it was before. But Webb can only do so much from 1.5 million kilometers away. What scientists really need is a spacecraft in orbit around Pluto, or better yet, one on its surface. As of now, no such mission has been approved. No orbiter, no lander is on the books. The journey alone would take the better part of a decade, and outer solar system exploration has rarely been treated as a funding priority. Missions closer to home return results within a few years instead of a few decades, and that trade-off means distant icy worlds consistently lose out. But that does not mean nobody is trying. Multiple research groups have submitted mission concepts proposing a dedicated Pluto orbiter, and some have explored the possibility of a lander capable of sampling the surface directly. Whether any of those proposals will ever be funded and built, nobody knows. Here is what stays with you when you step back far enough to see the whole picture. A 24-year-old farmhand with no university degree sat in an unheated dome nearly 100 years ago, flipping through glass plates 14 hours a day, searching for a single point of light that moved. He found it. And that faint dot, dismissed for decades, voted out of the planetary catalogue, written off as a frozen leftover at the edge of relevance, turned out to be a world with its own climate running in reverse, its own slow rain of biological building blocks, its own chemical exchange with a neighboring moon, and possibly its own ocean sealed away in the dark for longer than complex life has existed on Earth. We are standing on a warm speck of dust, orbiting an ordinary star, peering out to the farthest edge of our solar system through a telescope floating 1.5 million kilometers from home. And somehow, that was enough to discover that a forgotten dwarf planet has been quietly running its own system in total darkness with no one watching for billions of years. Pluto was never the dead end of the solar system. It was a door into the part that has not been written yet. And if one small, frozen, demoted world was hiding this much complexity beneath its surface, it is worth asking what is waiting across those trillions of other worlds we have never once looked at closely. Drop a comment and tell me which of these 4 discoveries surprised you most. The self-cooling atmosphere, the organic snow, the chemical exchange with Charon, or the possible hidden ocean. Share this with someone who still thinks Pluto is just a boring rock at the edge of the solar system, because it clearly is not. And if you want more, check out our video on Europa, because if you thought this was strange, you are not ready for what is going on beneath the ice over there. Thanks for watching. I will see you in the next one.